Hi and welcome to MSc. In this video we're going to be looking at function transformations, specifically identifying transformations from a graph. So here's an example here of a graph that's continuing on down in this direction here, and I have my x and y axes. Hopefully right away you can recognize the parent function that is represented here is the absolute value function. We know what the absolute value of the function looks like. It's a v, and there it is. We're going to try to figure out the transformations that have happened to form this transformed function. And we know that this can look like dilations or reflections in the x-axis. We know that there could be a k value. We know that there could be a horizontal shift, and there could be a vertical shift as well. So these are the possibilities that we have. So when I start looking at these, I certainly identify the parent function first, and then I start to just look and see what type of dilations or reflections I have. Reflections are usually pretty obvious, so I often like starting with those. This has clearly been upside down, flipped upside down, which means it's been reflected in the x-axis. So we can say from that the A is negative. Right? Again, it's that negative A value out front that will flip and reflect in the x-axis. I would not have any way of knowing with a symmetrical graph like this function if there was a reflection in the y-axis. I just wouldn't be able to tell that. On other functions, I would be a lot more obvious. We can't conclude that here, so we're just going to assume that there was none, which is a safe assumption because it won't matter either way. The other thing we can start to look at is now figuring out the dilations themselves. And we've seen previously that vertical dilations and horizontal dilations can appear as one another. Look at what the question asked. Most often the vertical piece is a little easier for students. I know I personally find that a little easier. And I think it's because of the opposite land that k lives in. So I know that a typical absolute value function has like an over 1, up 1 approach, right? As it go up, that absolute value function. So this one I notice goes over 1, down 3, over 1, down 3, and it goes down because a is negative. So it appears with that 3 factor that it looks like the absolute value of a is equal to 3. So we already have our a value. That's great. Now we can say our k value. Well, the k value is a little bit trickier because we've already dealt with our dilation and our reflections. But there has to be a k value there, because if k was just 0, this whole function would just be 0. So we can say that k is just equal to 1. Now we can move on to our translations. And our translations are where we know that this vertex point here usually starts right here at the origin. Somehow it's been shifted over 4 to the left and up 8. So the 4 to the left tells me that the d value is negative 4. And the up 8 tells me that the c value is 8. This is going to allow me to look at my transformed function t at x. And we know that the a value is 3. We can then say for the f, it's going to be the absolute value. I'm going to put a k value in here of 1 just for now, just to show you what that would look like. It would be bracketed out. You'd have x, and then the minus d is the negative 4. So it's minus negative 4, which is positive 4. Close the absolute value plus 1. Now it's silly to have this k value of 1 there common factored. And so it is much more common to see this expressed as the absolute value, or 3 times the absolute value of x plus 4 plus 8. And that is how we go about finding transformed functions from their graphs. Again, start with dilations and reflections. Be careful with the horizontal versus vertical dilation. Look at what the question asked. Watch for reflections in one or both axes. And then pick a point that you know well on the standard or parent function and figure out how it's been shifted to its new location. And that will give you your d and c value. I hope this short video has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you very much for listening and watching.